Institute for the next 2 years until 2012. And also she started there her PhD in quantum gravity under the supervision of Chris Smalling and Fidel until 2017, and then moved to Okinawa Institute of Science and Technology for the next 2-3 years. And in 2020, she started then her position at University of Brussels. And she also, I should mention, got a prize for her PhD thesis, which is called the John Brody Memorial Prize. And it's only one prize for a graduate student in co-perimeter for the originality, creativity, and independence in research at the Perimeter Institute. So we invited her. She's doing things that are in overlap with our interests, and she will report us about not yet on archive paper with Flaminia and Coulomb. Please.
Thank you so much, Czeslaw. Thank you everyone for coming to my talk. And so this is a collaboration work with Flaminia Giacomini, who was a PhD student from here, and Carlo Rovelli. And the paper should be online within a month or so. So the question we are trying to investigating is that what exactly is the quantum state sourced by quantum matter in superposition? How to describe the electromagnetic or the gravitational state in such a configuration? And so the reason why we are interested in such type of configuration, partially because, well, there is a lab that represents the world-class state of art in this building that has an ambitious aim of testing what is the quantum feature of the low-energy gravitational field. So the reason, one motivation is to connect with the tabletop experiment, and in the future, probably we are aiming at extract some non-trivial observation and prediction for such experiment. And so one example that already have been well studied is the gravity-induced entanglement. Which is a very elegant design to test the non-classical feature of gravity. And there have been a few papers from the group in Vienna analyzing this experiment. And our work could give a complementary perspective of this experiment. And another reason I'm studying this is because of the indefinite causal structure. And the first example in the gravity scenario also come from Vienna is the gravitational switch. And such configuration that you need to have the superposition of the semi-classical space-time requires a further investigation to see its quantum feature, and this is our work trying to address eventually. And theoretically, we are interested in the superposition of quantum geometry that's beyond this semi-classical superposition of the semi-classical state. So we want to see more feature of and also we want to understand what's the physical implication of this gauge potential, this Coulombic field of Newtonian field that many people thought, oh, this is just coming from the gauge. It probably, can it really carry quantum information? And our answer is yes, indeed. You can have a quantum state representation of this gauge, this Coulombic or Newtonian field. And we want to see how it can carry quantum information. So to be more feasible for the tabletop experiment, we do not want to use the formulation of quantum field theory because interacting quantum field theory, strictly speaking, is not well defined. Also, that's a formulation that is more suitable for, like in LHC, when you calculate S matrix, etc. So here, we only need to solve Schrödinger equation to get the quantum state in the Newtonian limit. And that will be sufficient for our description and easier connect to the tabletop experiment. And so I hope that from visiting the lab, the experimental lab, I can see that what kind of state that we can really prepare for the quantum matter, and we can further extract prediction for the gravitational field. Okay, so I will start from electromagnetism. The methodology, we are trying to parallel the electromagnetism and linearize the gravity as close as possible, but there will be essential difference. So in this talk, about 1 hour, I will go through all the essential steps for the electromagnetism, and that will be accessible to any graduate student. And for the gravity part, I wouldn't write down all the detail, but I will talk about the conceptual part and the physical implication. And then you can check the precise formula when our paper comes out. So the Lagrangian of electromagnetism with charged matter has the following form. And so here, just remind you that and our usually familiar electric magnetic field in terms of this vector potential is the following form. Under the gauge transformation, the vector potential transform as where epsilon is any arbitrary function defined on localized on each space-time point. And this is the infinitesimal transformation of the U1 gauge symmetry. So mm-hmm.
Or is this like a current that you put somewhere, like you have a wire?
It can be both. So you can see that this is a simplified version of writing. This is not gauge invariant. So to write it completely, it is the you can have the current of a completely free fermion field and coupled with electromagnetism. but in experiment, you also control the source. So it can be a given source.
No, I know.
There.
Which one of the two is being discussed here?
Oh, so the second one. So this J mu, when we quantize the matter, it will be an operator act on the quantum state of the matter. And if it's a superposition of the matter field that is under some control, like let's say electron with spin going through the magnetic field, and then we can calculate what's the eigenvalue of this current at the different position. And so, yeah, this is not a gauge invariant part. Strictly, it should be, if it's a scalar field, this should be and you get the J mu by doing functional derivative of the matter field configuration in the matter part of the Lagrangian. So we want to do the canonical quantization from the Lagrangian, and the step is to identify what's the canonical pair, what is the constraint, and then we want to solve the Schrödinger equation for this. And so for simplicity, in the Newtonian limit, this is the relativistic form. The J mu in the non-relativistic limit that we have a charge that the center of the mass momentum is nearly 0. In that case, we can approximate the Ji is much smaller than the energy configuration we care. And only the J0 component is non-trivial. I set the speed of light to be 1. And so the step 1 we need to do is a partial gauge fixing, because this is the interaction term in the Lagrangian. What we require is that the spatial derivative and under this partial gauge fixing, one could see that the Lagrangian becomes in the following form. The character is that, I will directly write down the Hamiltonian problem. So under this gauge fixing, this term dropped. And then we can do the Lagrange transformation to get from the Lagrangian to this Hamiltonian. The character I want to emphasize is that, this is G. Is that in the Lagrangian or in the Hamiltonian, there is, so in this gauge fixing, there's already no time derivative of the A0 component. The A0 worked as a Lagrange multiplier, impose a function is the constraint. And this constraint is exactly the Gauss law. So you can ask me more about how to quantize in constraint system. But technically, this is a secondary constraint, and it commutes with the Hamiltonian. So it is first class. And so this G is our familiar Gauss law. Just now, I also forgot to say that from the Lagrangian to the Hamiltonian, you do the Lagrange transform, and canonical conjugate momenta of AI is actually the electric field. Hence, the electric field and AI forms a canonical conjugate pair, and their Poisson bracket promoted to the commutator, and to find the representation of such canonical commutator gives us the quantization of the field. So when we promote it to the commutator, so if we want to write the quantum state in the representation that diagonalized the A operator, the notation will be let's say if I have an function of AI, it's A, and it gives me the eigenvalue and so the vector potential is not something observable. Eventually you need to extract the electro and the magnetic field from it. And the conjugate momenta will be defined from such a commutation relationship, will be the functional derivative of the vector potential. So then a wave function, right, in the representation of A where A represents the spatial part of the vector potential. The step of the quantization, so to get this wave function, you need to ensure it is the solution of the constraint. And it's the ground state of the Hamiltonian. Ground state of, if I write this Hamiltonian here, it will be it is independent of time, hence we are solving a standard stationary Schrödinger equation. Now we need to have a closer look of what is the physical implication of the Gauss law or the Coulombic field. So the physical state which satisfies constraint will be the one that are annihilated by the constraint. It is smaller than the possible kinematical state that is allowed. It is, so write it in the operator form. This will be, the Gauss law will be my wave functional in the vector potential representation. And so here, the J represents a linear sum of all the eigenvalue of the current. That my current is an operator, act on the quantum state of the matter, and I got a linear sum of the eigenvalue. We can do the Fourier transform and express in the momentum space of the vector potential. So that will be the Fourier transform of this will be what is this part really means? It is picking out the longitudinal mode. So if we have a wave or that's propagating, let's say the momentum vector is k, this is the spatial momentum. You can always decompose the mode as the transverse, that is orthogonal with my direction of the propagation and along the propagation. And so the Gauss law picks out the mode that is longitude with my motion. Far left, so here. How about this? So I will not use. Okay, I will not use this part anymore. So. Mm-hmm. So the Gauss law tells us that whenever we have a charge compared with just a vacuum electromagnetism, the physical effect of having a charge is such that I will have longitude mode in my wave functional. If I'm in a vacuum, we need to ensure there's no longitudinal mode. And so there's another way that is more insightful. So under a gauge transformation, recall that we only did a partial gauge fixing of the spatial derivative of the A0. So completely the AI part, the spatial part of the vector potential, have the full gauge invariant up to now. So under a gauge transformation, the wave functional we want to solve for the electromagnetic field will transform as following. Yes.
You had assumed at the beginning that Ji is 0, right?
Yes. Yes.
So this transformation is certain?
Okay. This is a good point I forgot to mention. So because of the Newtonian limit, Ji is 0. So the only non-trivial effect from the matter comes from this A0 imposed Gauss law. Otherwise, you will have the Moore term on the AI coupled with the AI part. And in gravity, we are paralleling doing the same, and the only non-trivial part of the matter is the T00 component that you will see later. so you are doing, if you do integration by part, you will get, actually, it's the Gauss constraint times this arbitrary function. Hence, a wave functional that satisfies Gauss law, actually, what it means that it is gauge invariant by itself. So as we already know, without charge, so the vacuum case, wave functional is independent with longitude mode. Hence, it is very convenient to use a projector into the transverse direction and solve the Schrödinger equation in the momentum representation. So this is defined as delta ij minus I'd write too high than what I can get. The Hamiltonian I just erased here. It's a quadratic Hamiltonian. It is p squared plus curl of A. So from a quadratic Hamiltonian, the standard ansatz of solving the ground state is to postulate a Gaussian, a quadratic order, and leaves the coefficient in the Gaussian to be free. So the vacuum state is in the following form. Well, up to some normalization factor. This, I will write a second line so we have more space. So when you solve the Schrödinger equation for the vacuum, the structure what you will get is the second order derivative gives you an integration of k squared. That's your eigenvalue of the energy. And then the square of the first order derivative will be the part cancels the curl of A part. And so at the end, this k is so the expression of the ground state, this we didn't invent. You could actually find in literature some time ago of trying to write the vacuum state of electromagnetism in this Schrödinger representation, but not using the second quantization of quantum field theory. And we can also write it in the, this projector, you can do a little bit of algebra to express the ground state in the more illuminating form. Which is a Gaussian state in terms of the magnetic field. So then with charge, we are adding the longitudinal mode to the wave function. The ansatz of solving the Gauss constraint will be, we use Q to represent wave functional with charge, will be the vacuum part times the I hope there's enough space. So this is the vacuum. This is the Fourier mode of the in the momentum space of my charge current density. So imagine if you have a localized point-like charge, a delta function Fourier transform is a constant. That will be constant in the momentum space. If you have like a coherent state of matter, you will get a non-trivial momentum dependent function. And so then we can get that with imagine with a localized charge in your laboratory desk, the whole wave function of the electromagnetic field, in this case will be the Coulombic field, will given by vacuum times the exponential of the longitudinal mode of my vector potential. Any question at this slide? In the electric field representation, which means you are doing a Fourier transformation from A to E, and then this exponential gives you a delta function of the Gauss constraint on the E times this will be a more illuminating form later for the linearized gravity, because what it tells us that if we have a Gauss constraint in the representation of the electric field representation, that finally the wave function will be a delta function of the constraint, means the electric field has to satisfy this equation, acting on the state that this will include the longitudinal mode of the electric field. So one can readily check that what's the energy eigenvalue. Of course, the vacuum part, you will get infinity and you need to normalize it. And the Coulombic part, the energy is contributed by the square of the two functional derivative on the AI. So from here, you will get the energy eigenvalue will be for completely point-like charge, the rho is a constant in momentum space. And you might recognize this 1 over k square is the momentum space, the Fourier transform mode of the Coulomb potential, of the 1 over r potential. So this whole energy is, I'm integrating the whole Coulomb field energy over the whole space-time. And of course, it will diverge for when you go close enough to the charge or your frequency is very high. And so what this says to the gravity-induced entanglement experiment, well, in the electromagnetic version, is that initially you have two particles that the internal degree of freedom is coupled with electromagnetism and goes through the electromagnetic field, comes into the superposition. I will use the black and white represent the two branch of the superposition. And then the Coulombic interaction between these two branches compare with the other branches, gives a relative different phase. And so the quantum state here experience the energy of this branch. Let's suppose this distance is d, and hence this gives the relative different phase of d square of d over e square. Coming from these two branches of the Coulombic or gravitational interaction. So, okay, I will not use this part or erase this part. And now we are ready to look at gravity. Is there any question at this point? Yes. Yes. No. So this is weaker than Coulomb gauge and the Lorentz gauge. So actually, in our work, initially we completely fixed A0 equal to 0. That's a temporal gauge. Then we realized we actually do not need it. We only need the spatial derivative. So make A0 a constant in the whole space-time. And then this A0 worked as the Lagrangian multiplier, imposed the Gauss constraint. And the conjugate momentum of A0 is 0. Hence, from the Poisson bracket of conjugate momentum of A0, this primary constraint conserved in time, we get the Gauss law as the secondary constraint. And so if you fix the Coulomb gauge, you are actually you are eliminated completely to the 2 degree of the physical degree of freedom. And you impose on the AI. And in that case, that further, the Coulomb gauge is a second class constraint. It doesn't commute with this, and you need to use the Dirac bracket to do the quantization. But I think in that way, you wouldn't get, the wave function will be a slightly more constrained form, and the Dirac quantization has more complication, but it's doable in the Coulomb gauge. We are trying to parallel the case of electromagnetism as close as possible, and as a linearized theory, this is theoretically very solvable. It's different with the full background independent quantum gravity. So because we want the Hamiltonian formulation to solve the Schrödinger equation, the most convenient use is this 3+1 decomposition of the gravity. So this is slicing our space-time manifold to a branch of the 3-dimensional hypersurface. To relate this slicing, there's 2 gauge parameters. One is called lapse, the other is called shifts. What it does is you imagine this is like a branch of lasagna, and you need to identify, you put the toothpaste through the lasagna and identify where is on my spatial manifold. Am I calling it the same point? So from this layer, move to this layer, I'm identify this point, move to this point, and the gauge parameter corresponds to my freedom of choosing the coordinate. This is called, I always mix words, this is lapse, this is shifts. And so in this decomposition, any arbitrary metric is written as the following form. So we are doing the linearized pretermation over flat space-time metric. So here is a subtle point, is that because we already fixed the underlying, the leading order of the space-time to be Minkowski, it becomes a X-independent fixed structure. Hence, then you do a perturbation on the lapse and the shifts, that will have actually a extra partial gauge fixing on the lapse and shifts due to the perturbation over Minkowski. And under this perturbation, the lapse, this expansion is in terms of kappa is 16 pi g over, let me find. Yeah, I think it's this. The zeroth order of Ni is 0, and the leading order is already the perturbation order. In order to recover the leading order of the Minkowski from this general space-time metric. So then you can go from, we calculate both of the perturbative expansion of the full ADM Hamiltonian, or the or you don't need perturbative, but 3+1 decomposition of already the linearized gravity action, you get eventually comes down to the following form of the action. You need to so parallel to this, we need to gauge fix so this does not fix the value of the perturbation of lapse and shifts, but require it to be a whole space constant function. And this was coming from previously I mentioned that you are perturbating on a fixed space-time metric. So under such a partial gauge fixing, you can put the action of the linearized gravity is also in terms of this Lagrange multiplier times secondary constraint form. So we expand the action to the second order. What you get is there's 6 terms of quadratic. It's all in terms of partial something h, partial h, or the trace of it. It's very long. I will not write it in detail. Plus electromagnetism, we only have the Gauss law, one constraint. Here we will have 4. This will coming from the leading order of the perturbing the Hamiltonian constraint. And this will come from the spatial diffeomorphism part. So in the linearized theory, this generates the spatial diffeomorphism invariant, and this generates the time translation part. And the form, let me erase. The canonical conjugate pair is my spatial part of the metric with the conjugate momenta, pi k L. This will be it forms my Poisson bracket. And under this bracket, we can check that the linearized constraint actually commute. They are all first class. This is different with the full nonlinear gravity. And more explicitly, I will show you the form of the constraint. So the scalar constraint a time derivative here. Kappa is this. This is when the only way matter field shows in the Lagrangian. I think I might have forgot at the beginning to say that the interaction term of the linearized gravity will be and the stress energy tensor of my matter field shows up in the constraint. And again, we are assuming the Newtonian limit, the spatial momenta of the matter is negligible. In that situation, we can remove this part to simplify. And the only non-trivial component of a matter source comes in my scalar constraint. When one analyzing the linearized gravity, it's always illuminating to decompose the perturbation, the fluctuation of my metric, again in terms of the transverse or longitude mode relative to my propagation momenta. So Hij symmetric tensor has 6 components, and it has 2 transverse traceless degree of freedom. So the some question. So when we decompose, the longitude mode along with my momenta satisfies, I should say the transverse part satisfies and under this decomposition, one can show that the scalar constraint is only constrained on the trace part of the transverse mode.
There's no H dot in C?
No. So the momentum direction on the transverse decomposition, the trace of the transverse need to satisfy this for my matter degree of freedom. And you can recognize this is standard Poisson equation, and the solution of this gives you the Newtonian field. This gives you, let me see whether it is. The Newtonian potential with an arbitrary function, this needs to be the solution of harmonical function, satisfies the source free. Actually, if you don't have any matter, the HT can be up to any arbitrary harmonical functions in the longitudinal mode. And the scalar constraint is actually expressed as and this might ring a bell if you have a good memory for the electromagnetic case. This is exactly parallel the Gauss constraint in the electromagnetic field. Recall that in Gauss constraint, we have act on the wave function gives 0. And this ensures that my wave functional is invariant under the spatial Yuan gauge transformation. And so here, similarly, we need to ensure that the wave functional in the metric representation satisfy the scalar constraint. And one could check that this C actually generates the spatial diffuse within this wave functional. If you are doing a gauge transformation on the wave functional, the infinitesimal version for the linearized gravity is the following form. Again, integration by parts, you will get which, under the imposition of the scalar constraint, it vanishes. And why the state is independent of the longitudinal mode? Because for the mode, this can longitudinal mode that along with my momentum vector, it can always represent by, it's actually 3 degrees of freedom. represented by one space vector, which has 3 components of the symmetrization of it. And so satisfying this constraint means this imposes that my perturbation is completely gauge invariant under the spatial diffeomorphism, and it has to be independent of the longitudinal mode. And now I think you immediately have the answer that the vacuum state needs to be the ground state of the Hamiltonian, that the ansatz needs to be a Gaussian state that subtract all the longitudinal mode, like what we did in electromagnetism. Okay, time is up, so I'll go rather quick. And then when we add matter, the only non-trivial part is we need to constrain the trace part of the transverse mode to satisfy the constraint. And classically, it has this solution. So for the people who are familiar with gravitational wave physics, they are always solving everything in they call it transverse traceless gauge. So they set everything else to be 0, and the only non-zero part is the transverse traceless. This wouldn't be suitable for the case with a matter source that we are trying to solve the quantum state of the Newtonian potential. It's exactly because here that you can see we cannot fix a gauge to kill the trace of the transverse degree of freedom. That will be killing the Newtonian potential. So eventually one can write down with the matter constraint, it's the delta function of the scalar constraint times the exponential of the Gaussian by the transverse mode. And so this part, take it as a grain of salt because I still need to go through many consistency checks to ensure this is the correct wave functional and need to recheck the numerical coefficient. But the form would be here the numerical coefficient I need to check. So it will be this is that projector. Project the momentum space Fourier mode of my metric perturbation into the transverse direction. But here, as a tensor, we have 2 parts. We have the transverse of Hij, and we also have the trace part. Because in the Hamiltonian, the part I didn't write down. Well, actually, that Hamiltonian, we do the linear expansion and calculate many times to converge to that answer, because every time there are some small mistakes. And so that Hamiltonian, that will be the pi square, momentum square of the transverse mode minus the pi square, half of the pi square of the trace of the transverse, and plus the kinematical terms such as partial KHIJ square. And this will be similar as if you have a scalar wave, the partial mu phi, this kind of term. And then there's also a part of the longitudinal mode that will be, that the wave functional need to be independent of. And so, okay, I think this is all the technical detail of our work. And so I really think that it can open some possibility of investigating other property strategy of testing the quantum feature of gravity. So for example, I never thought anyone have tried that idea, but one could try to check whether there's a gravity-induced contextuality, that we are doing the different measurement of this gravitational state sourced by matter, and we need to define what's our POVM, what's the possible observable we could measure, and check whether there's a gravity-induced contextuality that might be a very nice evidence of the non-classical feature of the gravity. And okay, looking forward to discuss with all of you on the other possible ideas. Thanks. Oh, yeah. So here, the wave functional I showed is like a one matter source with the quantum state. And then we know the quantum theory of the matter source. And you can get the eigenvalue of the current. Let's say you can get the eigenvalue of the current in terms of a wave functional of the matter that is in, let's say, in a coherent state or in some other form. And then you Fourier transform, you get this, you get the Gauss law or Newtonian constraint to solve for the quantum configuration of the gravity or the electromagnetic field. And this is all completely doable. And then it will encode, it will be like the quantum degree of freedom of matter encode in the wave form of your Newtonian field. And so this allows us to study arbitrary perturbation we have on the flat space-time of arbitrary matter distribution as long as it is in the Newtonian limit. The state it can be rigorously written down and further analyzing its physical consequence. And so for the simplest case of the superposition of two locations, that's just a superposition of the two density of the charge at the different location. It's completely linear.
That case would be the superposition of semi-classical space.
Yes, yes, this will be, yeah.
I have a potentially very naive question, which is something I would expect for in a sort of lowest energy approximation of quantum effects in gravity would be a kind of an understanding of observables more in the sense of sort of standard non-relativistic quantum mechanics rather than in the direction of field theory. So, I mean, if you understand that one could say, okay, well, the configuration of the gravitational field is an observable, if I understand correctly, in the formulation that you laid out. But I mean, I don't, like, from a very operationalist perspective, I don't have like a...
Yeah, this is a great question.
Detector that's like, oh, the 1-2 component of the metric is equal to 3.
Yes, this is a great question. The simplest observable is the proper time. You can perturb the space-time a little bit by the mass and check how the proper time by a quantum clock or something. Or particle that go through like the Aharonov-Bohm phase to detect this change. And so there's also this non-commutativity of the perturbation of the metric and its conjugate momentum. And so this non-commutativity of the conjugate variable like x and p, these will have some physical effect that so far we haven't explored yet.
Okay, but so the key physical observable, the key sort of operational observable you're looking at is the prototype?
Yes, I think the simplest is the prototype.
If I remember correctly, you were saying you can also study indefinite Cursus structures.
Oh, so that's a motivation, and so this gives the space-time configuration of I have the mass on the left and the right, and so in the gravitational switch we put an Earth, and so that part, I can explain a little bit more later on that configuration, like superposition of Schwarzschild geometry, how it fits into this gauge of the formulation. But if we don't have the superposition of Earth, we have superposition of the two quantum particles, then this gravitational state in principle gives us this gravitational switch space-time configuration.
So you can cast basically any center with a matter source into this quantum.
Yes, any matter in the Newtonian limit. And we also think it's easy to go beyond the Newtonian limit by turning on the longitudinal mode, but we don't have to for the tabletop experiment. Okay.
So, and also to clarify the kind of limits that you're talking about, so in this formalism, there's no the extent of a mass in superposition, for example, is kind of irrelevant as long as the mass is small enough, as long as the mass energy is small enough that you can remain within what would, in the classical approach, be the Newtonian limit. This formalism can still be applied to arbitrarily large superpositions. Is that right?
Yes, the approximation is that the spatial momentum of the mass is small. We don't have like a fast-moving particle. Right. As long as anything in this room we can do, it can be very massive, it is fine. But of course, if your mass density is huge, the perturbation of the gravity will break down.
Right. Yeah. But the limit there is really just the same limit of approximation as in the classical theory, right? It has nothing to do with the quantization theory. Or does it?
You mean for the mass configuration?
Well, I think it's maybe, so like with the what's it called, semi-classical gravity, where you take the average of the quantum field tensor and then plug that into Einstein's equations. This doesn't work for very large superpositions. If your mass is unique, we'll say the great advantage of what you're doing is you can go beyond this.
Yes, goes beyond this expectation value of the stress and.
But I'm wondering what are the bounds of this method? Is the only limitation? It seems like, as I understand it, the only limitation of this is really the same limitation as when you want to use an Newtonian approximation for classical gravitational calculations. That's my real question. Is that?
Yes, I think so.
That is the Newtonian approximation.
Yeah.
Or is there something else within the quantization that somehow missed?
When you're doing the linearized gravity, the gravitational field cannot be very strong, means your mass density cannot be too huge, otherwise create small. Yeah.
It's the same limitation as classical. The Newtonian approximation itself, what I'm saying.
Yes. Yeah. Thanks.
Maybe I can actually repeat the question in some different form. It came again and again, but I don't know now. I'm a little bit confused. So you mentioned that momentum of the matter
Yes.
is neglected. Is it true?
Momentum of so the speed of the matter is much smaller than the speed of light in the non-relativistic limit.
But you keep momentum of the source.
Yes, the momentum source comes in as you Fourier transform the current. If your current have a non-trivial distribution on the x, you Fourier transform, it will have the momentum dependent on the momentum space, but for very small momentum.
one point you said Tij components are T0.
Yes,
Components are reactive.
yes, because the T mu nu is composed by the U mu U nu, the full velocity of the matter, and so in the Newtonian limit we only use the T00. Even T0I we dropped, but that can easily turn down by, this is proportional to T0I. Yeah. So I would say that for slightly fast moving matter, if we turn on the T0I, then it will be not just the Newtonian field, then it will have some longitudinal mode in the wave functional. Mm-hmm.
One of the, I mean, sorry to ask my question, but one of the big discussions that has been going on the past 4 years was to understand how to describe the degrees of freedom that would be mediating quantum information, because that's a claim,
Mm-hmm.
right?
Yeah.
But if you do that, there's no degrees of freedom, right?
You mean no degree of freedom? So if you fix the gauge completely, let's say,
No, if you just keep T00, just there cannot be any retardation in your feed rate. Am I wrong? That's what I'm not sure. What
the T0,
turning on the longitudinal part.
the T00 is only the energy of the matter, and so that doesn't influence my Newtonian field to carry the information. So the quantum state I'm solving is the.
Is there anything more than Newtonian field in your age?
No. So here only the Newtonian. Yes. So indeed, so here we do not have propagating mode in the sense of like if you have a charge accelerating, it will emitting gravitational wave, and that part.
Right, so you still have to assume locality on top of it to make because if there's no space-time locality, the argument doesn't go through, right?
Yes, there is a need to
So
have.
you have to assume it in addition to this formula, or is it already there?
I think space-time locality is already in the linearized gravity when we quantize it. It's already.
In this approximation you're getting.
Probably I didn't fully understand the question. So you mean the Newtonian limit will need to assume related to space-time locality.
Variation of Hij, but I'm confused with how it works. So you said there's no propagating degrees of freedom, right? But if there are no propagating degrees of freedom, there's no mediation.
So so usually the gravitational wave, that degree of freedom is hidden in the ground state, in the vacuum part. It's the transverse trace degree of freedom. And then for the Newtonian matter, this part you don't see you see the vacuum as a stack of the plane wave, but you do not see the extra gravitational wave. And then when you have the Tij and Ti0 turns on, and with the non-trivial matter source in the non-trivial motion, then you will see that part of the radiative degree of freedom.
So there are the transverse traceless.
Yes.
How are they sourced?
So in the Newtonian limit, it's not sourced by matter. It is the vacuum state. So in the wave functional, we have a projector of H, I, J, P, I, L. So when we do this kind of projection, it projects H to the transverse degree of freedom.
That's the definition of what is this in HTT. But what I'm asking is there the mechanism by which the transverse traceless part is created by what you're doing to the matter, or are you just going to postulate that?
That part we postulated as we don't have that matter creating gravitational wave part of the interaction.
So
Yep.
you will say that it must have created an HTT. Right. Okay.
So the HTT here is become matter independent because the only part matter runs in is the Newtonian field.
Good, maybe that's the point. Stop. And then we continue directly the discussions. Okay, thank you very much.
Thanks.
Very nice. Thank you.
So nice.
So here you have like the Laplace equation,
Yes.
but here you have Schrödinger.
Oh, sorry.
So this is a trick.
Yes, this is a Poisson equation.
Poisson equation. So there are no h dot terms or h dot square terms because they are a different order in coupling or something.
Dot.
Or h dot square.